thank you guys for coming up and be here. I'll start right in. This is perhaps the most iconic image of man-made climate change, the rise of CO2 as monitored at Mauna Loa Observatory, started by David Keeling. I want to draw your attention to the seasonal cycle. When you look at it, you can eyeball that currently the peak-to-peak amplitude of the seasonal cycle is about 7 ppm. This is actually fairly representative of the average of the Northern Hemisphere. And 7 ppm seasonal cycle in the Northern Hemisphere corresponds to net ecosystem seasonal uptake of about 7 billion tons of carbon. So you can compare that with man-made emissions. The burning of fossil fuels currently is annually about 10 billion tons of carbon. So in other words, we humans, we emit more every year than the seasonal uptake of all ecosystems in the Northern Hemisphere. Forest, crops, everything. Stunning. The black line is a deseasonalized trend created by removing a 7-year average, moving average seasonal cycle. So we'll take a look at that first. We can look at the seasonal cycle by looking at both CO2 and C13. If you plot it in this way, on the y-axis the product of the concentration and the isotopic signature, and on the x-axis the seasonal cycle of CO2 itself, then the slope of this plot gives you the apparent isotopic signature of the sources and sinks that are being added and removed during the seasonal cycle. And the apparent signature is 27 per mil. On average, over the time period to which this plot applies, it's about from 93 to today. The CO2, the C13 signature of the atmosphere was about 8.3 per mil. So this would correspond to the cause of the seasonal cycle being something that fractionates with respect to the atmosphere by 18.7 per mil. This is purely the terrestrial biosphere. So this is proof that the seasonal cycle is really entirely resulting from land plants. Now we go beyond the seasonal cycle and we look at the wiggles of the black curve on the first plot. And you take the time derivative of that, then on the upper plot you have the growth rate of CO2, where the seasonal cycle has been removed. And in the bottom you have the rate of decrease of global C13, the C13 signature of that CO2. And it has a downgoing trend, because we're adding, of course, fossil fuels, which are depleted relative to the atmosphere in C13. But if you look closely, you see that, certainly in the last part, the average annual growth rate is 2 ppm, and on the lower plot, you see that the rate of decrease of C13 is minus 0.3 per mil per year. This may seem odd, because the signature of fossil fuels is not 7 per mil relative to the atmosphere, which would give you, a low rate of decrease of C13. So this is a problem that crops up in interpretation of C13 data. You see it regularly. Actually, I see it regularly. I can explain why this is. Or you can see it. If you realize, if you think about the following thought experiment. Suppose we were to somehow magically replace all C12, CO2 in the atmosphere today by C13. So the atmospheric CO2 would consist solely of C13O2. Nothing else changes. So And we also assume that the atmosphere is in equilibrium chemically with the oceans. The C13 signature would disappear quickly, because for every C13 going into the ocean, a C12 would come out. And so the C13 signature bleeds away. Whereas with our assumption of the atmosphere and ocean being in equilibrium chemically, CO2 doesn't budge, it doesn't change at all. So there's something about C13. The signature bleeds away much more quickly than the CO2 that we add to the atmosphere, which is the CO2 that we add to the atmosphere is hampered going into the ocean by the so-called buffer factor. And C13 is not being hampered by that. So let's go one step further with this. So if I take away the long-term trend of the growth rate, so the minus 0.03 per mil, and the 2 ppm rate of increase of CO2, and I plot the CO2 curve, the interannual variations of the growth rate in black, I can overplot the interannual variations of C13 in red, but scaled by a fractionation factor of 20 per mil, and they pretty much overlap. So once we have gotten rid of our confusion about how C13 works, we can see that the interannual variability of the carbon cycle, as seen in the atmosphere, is also almost primarily driven by the terrestrial biosphere. All right, now we're going to go from natural variations to man-made variations. This is the 800,000 year Antarctic ice core record with, at the end, modern CO2, like a straight line vertical. So what we see today is truly exceptional. But not only the concentration is exceptionally high and anomalous really compared to Earth history, also the rate at which the CO2 is changing is highly anomalous. On the left you see the CO2 concentration as it changed with the Earth coming out of the last ice age. An increase of about 75 ppm or so took 6,000 years. Whereas on the right-hand plot, you see the same Keeling curve I showed you earlier, and it's 85 ppm increase there during the time of direct CO2 measurements in the atmosphere in a couple of decades. So the rate of increase today is about 100 times faster than when the Earth climbed out of the last ice age. One more sign of human domination. Even if we didn't know that we were burning fossil fuels and we looked at the atmosphere, we can diagnose what the source is. And so what you see plotted here is a history of C13 CO2 in the atmosphere, first from Fern and ice cores, and then modern day measurements at the end, with a sharply downgoing trend there. If the additional CO2 that we see in the atmosphere, if it were to come from the oceans, C13 would not have changed. If, as has been alleged by some climate deniers, if it had come from volcanoes, C13 in the atmosphere would have increased. But we see that that's not the case. It goes down, and it is actually fully compatible with a depleted source of organic material of, roughly 20 per mil, different from the atmosphere. And in addition to that, when we plot the difference between Mauna Loa and the South Pole over time, again deseasonalized, so this is the long-term trend of both, we can see that the difference between the two hemispheres has changed gradually over time. And it's always higher in the northern hemisphere. So this is consistent with a source that is primarily in the northern hemisphere and has increased in magnitude roughly fourfold over the last decades. What could that be? And here in cartoon form, what I just showed you in the last 4 slides, roughly a carbon budget, atmospheric carbon budget in 1960 and in 2010, 50 years later. The width of the arrows is proportional to the size of the flux. You see, as we go forward in time, that the fossil fuels have truly come to dominate the carbon cycle completely. Even biomass burning, which was a very significant contributor to atmospheric increase in the first part of the industrial revolution, it has slightly decreased during the last decade, and maybe before. It's almost insignificant compared to how much we burn by burning fossil fuels. Now something else first. This is also apparent actually in the IPCC report, even though it's not so clear, at least in my opinion. What you see here is CO2 according to the 4 representative concentration pathways as the IPCC has defined them. What you see here is the amount of fossil fuel CO2 that we can emit as a function of time, taking all the climate and carbon feedbacks that we have modeled into account. And that gives you the fuzziness. Like some model will have a positive climate feedback or carbon feedback, it warms and the terrestrial biosphere and the oceans will lose carbon. That will then allow us to burn less to stay on the same predefined representative concentration pathway. But the most important point here is that we can all see what the big driver is of future CO2 increase. It's fossil fuel emissions, by far. By the way, the historical record, it's portrayed in the gray curve until 2006. It's also fuzziness about it. This is funny. Basically, we know, of course, exactly what the pathway was. It's basically that these models are not all that good, actually, in also portraying the past, what happened in the past. So it would certainly decrease my faith in these projections for the future. Okay. Now this is a diagnostic model of where it might have gone. Red is the emissions, cumulative emissions. Black is the atmospheric observed increase, cumulative. And then blue is an ocean model portraying uptake of CO2 by the oceans as the atmospheric CO2 increases. And the blue curve has been forced, the model has been forced to go through the 1995 total anthropogenic inventory of CO2 in the oceans from the Woes-Jacobs cruises. And the slope also is fixed. It has to be consistent at least with Ralph Keeling and co-workers' estimates of the O2 N2 change in the atmosphere. It has to be consistent with that. And so what you see here to a first approximation that what we have emitted is approximately equal to the increase in the oceans and the atmosphere, with a very small contribution of the terrestrial biosphere, which is plotted here as a residual to have mass balance. Then I take this model into the future, and I claim that CO2 in the future will be primarily determined by what we humans emit. And I'm assuming here that the total cumulative emissions will be, in the end, 900 billion tons of carbon. So we're basically, now we have emitted about 400 billion tons of carbon, so we are almost at the halfway point. Atmospheric CO2 will be permanently very high, even though, the oceans and the atmosphere are still equilibrating for hundreds of years. But atmospheric CO2 will not go down below 350 for more than several thousand years, actually. In this simple model, where I assume that the partitioning, that this is purely based on chemistry, is well known actually. So I'm not talking about the biology in the oceans perhaps being different, presenting different PCO2 to the atmosphere. All of that is possible. Ocean circulation will probably change, but I'm not going to predict that. This is just a prediction with what we know. And here's the kicker. Now suppose, instead of, I had assumed in the previous that the terrestrial biosphere wouldn't change anymore. It doesn't make a large contribution. But suppose that the terrestrial biosphere, either all by itself because of CO2 fertilization and nitrogen fertilization, or because we humans want to mitigate emissions by putting it in the terrestrial biosphere in various ways on purpose. So I assume that there's a 1 billion ton of carbon net uptake by the terrestrial biosphere here over a period of 100 years. Well, also that benefit will distribute itself between the atmosphere and the oceans in the same proportion as the emissions are in the long run will be distributed by the atmosphere and the oceans. And so 83% of that benefit of decreasing CO2, mitigating CO2 will end up in the oceans, and only 17% will be in the atmosphere. That makes our task of trying to mitigate CO2 very difficult. It's not enough to just pump it out of the atmosphere. We have to pull it out of the ocean as well, somehow. So here's the upshot, I think. You can read the conclusions. Since the atmospheric CO2 enhancement will stay so long in the atmosphere-ocean system, there will be plenty of time for very slow feedbacks that we do not know very well, or not at all, to come into play. And so I think that we really have no choice but to try to get rid of our need to grow the economy every 2 years, every year by about 2% or so, which seems to be sort of the desirable growth rate. Unfortunately, our economic system is built to need that kind of growth to actually function properly. And yet, it is the cause of our problems in the long run. This will do us in if we don't manage to change this. So I want to make a plea for ourselves, but also for economists, to come up with something better that will allow us to get out of this bind. I'll stop there. Questions?
Time for a quick question.
You have to use the microphone because I'm half deaf.
Hi, Peter. Thank you. Just wondered about, you assumed that over the next century you could have a 1 gigaton terrestrial carbon storage. Is there any chance that number could be significantly higher?
Yeah, it possibly it could be higher, but still, suppose it were 3, then still 83% of the benefit would still disappear also. This was just illustrative. Although maintaining a net uptake of 3 billion tons over 100 years, that is tough all by itself. I think very tough. But no, I cannot exclude it.